This panorama was taken by Curiosity rover while the rover was working at a location inside Gale crater. The very first X-ray diffraction analysis of Martian soil was performed at this location. The results from the rover's chemistry and mineralogy analysis revealed the presence of several minerals including feldspar, pyroxenes, and olivine, and suggested that the Martian soil in the sample was similar to the weathered basaltic soils of Hawaiian volcanoes. Later, Curiosity rover also detected abundant, easily accessible water 1.5 to 3 weight% in soil samples at this region. In addition, the rover also found two principal soil types, a fine-grained mafic type and a locally derived coarse-grained felsic type. The mafic type, similar to other Martian soils and Martian dust, was associated with hydration of the amorphous phases of the soil. Also, perchlorates, the presence of which may make detection of life-related organic molecules difficult, were found at the Curiosity rover landing site and earlier at the more polar site of the Phoenix lander, suggesting a global distribution of these salts. Many shallow irregular pits with raised rims concentrated along ridges and other topographic features can be seen in this view. But how did these odd features form? One idea is that they could be from sublimation of shallow lenses of nearly pure ice. But why do the pits have raised rims? They can't be impact craters with such fortuitous alignment and irregular margins. They also aren't wind-blown deposits because there are many boulders too big to be moved by the wind. There are other younger wind-blown drifts on top of the pits, and there is no clear connection to volcanism either. Some speculate that there were ancient oceans over this region that could somehow explain these features. Ancient glaciation is another possibility, perhaps depositing ice-rich debris next to the topographic obstacles. Perhaps future images of this region may provide clues, but for now this is a mystery. In this promontory, which juts out of the walls of Victoria crater, we can see that the upper portion of the crater wall contains a jumble of material tossed outward by the impact that excavated the crater. This vertical cross-section through the blanket of ejected material surrounding the crater was exposed by erosion that expanded the crater outward from its original diameter. Also below the jumbled material in the upper part of the wall are layers that are relatively intact from before the crater causing impact. Near the base of the promontory are layers with a cross-bedding intersecting with each other at angles rather than parallel to each other. Large-scale cross-bedding can result from material being deposited as wind-blown dunes. This interesting hill within Endeavour crater's rim is where many clay minerals have been detected from the orbit. The hill includes a rocky outcrop where Mars rovers have found concretions of small spherical features reminiscent of but different from the iron-rich spheres known as blueberries. The blueberries are concretions formed by the action of mineral-laden water inside rocks, but that is only one of the ways nature can make small rounded particles. The newly found spherules at this hill, which are about an eighth of an inch in diameter, have different composition and internal structure. Scientists have a range of theories about the possibilities for how they formed. One working hypothesis out of several is that these spherules are also concretions like the blueberries but with a different composition. Others include that they may be accretionary lapilli formed in volcanic ash eruptions, impact spherules formed in impact events, or devitrification spherules resulting from formation of crystals from formerly melted material. This rock outcrop has piqued the interest of Mars scientists. The outcrop has pale mudstone at the bottom of the outcrop, which meets with coarser sandstone in a geological contact zone. Due to this, the white mineral veins that fill fractures in the lower rock unit abruptly end as they meet the upper rock unit. Such clues help scientists understand the possible timing of geological events. In this case, the fine sediment that now forms the lower unit would have hardened into rock first. It then would have fractured and groundwater would have deposited calcium sulfate minerals into the fractures. Next, the coarser sediment that forms the upper unit would have been then deposited. The whole area pictured here is about 16 inches across. Curiosity rover took this selfie after its recent drilling operation at a site on Mount Sharp. Each layer of Mount Sharp is a piece of the puzzle that offers clues to Mars' history. The two recent drill holes on the bedrocks are visible to the lower left of the rover in this view. The rocky spots of the area here have various bedrocks but also pebbles and slowly moving sand. The results of sample analysis from drilling operations like these will be helpful in deciding how to continue the research in the area. The plan is to carry out more drillings in the future, but it also depends on which spots will reveal the most interesting features. Different areas show different geological features, and the research will be conducted in order to obtain the most complete information on the complex history of Mount Sharp and Gale crater. Perseverance rover took this video as it traveled over the Martian surface. During this journey, Perseverance drove from a crater floor onto a delta, which has a vast expanse of 3 billion-year-old sediments that from orbit resembles the river deltas on Earth. While descending a hill, NASA's Mars rover took this most detailed panorama of the inner basin, the rover's next target destination. The rover acquired this more oblique view known as the Seminole panorama from about halfway down the south flank of the hill, 164 feet or so below the summit. The two hills seen near the center of the panorama on the horizon are McCool Hill and Ramon Hill. An arc of rover tracks made while avoiding obstacles and getting into position to examine rock outcrops can also be traced over a long distance in the panorama. Long linear ridges and grooves curve, wave, and buckle across most of this view. Here, as elsewhere on Mars, these linear ridges and grooves fill a valley floor, therefore they are known as lineated valley fill. Because these features are only found in valleys in the middle latitudes 30 to 60 degrees of the northern and southern hemispheres, scientists had long suspected that they were associated with some ancient climate that had prevailed in the latitudinal band. Based on peering beneath the surface using radar, Scientists now think that lineated valley fill is probably merely a rocky veneer atop a glacier of nearly pure ice. The rocks that make up the linear ridges and grooves were oriented by the ancient flow of the glacier underneath.